Yeah, welcome back, everybody. So what we're going to talk about now is what we term as intermediate Linux. And so this session is basically intended for anyone who works in a Linux environment and wants to acquire additional skills to more effectively use advanced cyber infrastructures. So a little bit about particular file system hierarchy standards, symbolic links and hard links, wildcards and globbing, aliases, environment variables, configuration files, pseudo file systems, and bash scripting. So we assume that you already know the Linux basics, such as listing files, removing files, navigating directories with ls or mcd commands, listing file contents with cat and optionally head and tail, or less and more, and ability to use one or more of the standard editors, which means, this usually people know either VI or Vim and Emacs or Nano, but nowadays there are many more different editors, but these are the ones that are usually by default installed on any systems, particular VI, and relative and absolute paths. So we're not going to talk about any of these. And then just a quick note on what is intermediate Linux. So that's certainly in the eye of the beholder. Everything that we are covering in this session would be considered basic, right, by Linux systems administrator or somebody who is, been using Linux for a long time. But if you're attending this session, you're probably not a sysadmin, or you might not be using Linux on a regular basis. Maybe you've been using mostly Windows systems, it's more likely you're a student, an educator, or researcher who uses advanced CI as part of your work or studies, and not everybody's a Linux expert. In which case, these topics would probably be intermediate in the context of Linux users instead of Linux professionals. So there's always, it's always the case that, content of some material might be boring for somebody else and advanced for somebody different. We hope that this is useful for some of you, and more often than not, I find myself sometimes learning something new when I listen to somebody else, because I got used to doing something and there might be a better way that I just never looked into, simply because things were working fine the way I was doing them. If we're talking about the file system hierarchy standard, it describes the conventional layout of a Linux system. There are some variations among different Linux distributions, but they tend to be pretty minor and mostly related to the lib, bin, or user lib and user bin directories. So as a regular user who doesn't need to administrate systems, you don't need to know too much about the file hierarchy standard. We're covering it here to round out your knowledge and make the Linux environment a little less mysterious. There are links here for overviews. Simply, you can go on Wikipedia and read about it, or there's more deep dives in the Linux documentation project, for instance, tldp.org, that's been around for a long time, or Linux Foundation has, of course, a lot of information. So the most important directories probably are the home directory. So everything's relative to a root directory that's indicated as slash. And then relative to that, you have different directories, and /home contains the user home directories. Then there's bin and user bin that traditionally contain essential and non-essential command binaries, but these are often merged. So on CentOS Linux, for instance, /bin is a symbolic link to /user /bin, right? So it's effectively the same directory actually. And sbin and user sbin contain system specific, system administration binaries that are required actually to bring up the system and administrate the system, right? So not necessarily used by users, but required by admins. Like bin and user bin, these are often merged by a symbolic link. And then we have /lib and /userlib, which contain libraries that are needed by Linux commands. So they contain either dynamic libraries that are linked at runtime, or static libraries that you can link at compile time to a code. And /opt is where software was traditionally installed, sort of like optional packages. But with the rising popularity of package managers like SPAC, this directory is not used much anymore. It really depends. You know, I personally sometimes still put software in there. And some package managers on the Mac OS actually put software in there. etc contains configuration files for Linux shells, schedulers, networking, accounts, package managers, and others. /root is the home directory for the root user, so the system administrator. And then /var here says log files. Really, it's anything that's variable during runtime. So those would be files that are expected to change while the operating system is running. And so more often, you will look into something /var/log, and then there's log files in there that you can inspect to see if everything's working as expected or if there are some error messages. And then /dev is the device files for terminals, disks, networking, etc. And /proc and /sys are these pseudo file systems that we've already seen before that contain information about the running processes and the hardware that's handled by the kernel. And finally, there's /tmp. That's usually limited in size, but it stores temporary files. So it's basically gets often automatically cleaned up. So upon reboots or after certain amounts of time. So it's just meant for temporary file storage. Not everything fits into the file hierarchy system. So especially in the high performance computing environment, this can include additional files and file systems and software installed using package managers, like I just mentioned. For instance, on SDSC's Expanse, we have this lasted parallel file system, and that is mounted under /expanse/projects, for project storage, and /expanse/scratch that is meant for doing IO scratch operations and or storing temporary data that you don't need to keep right after running your job. Then we have the Cumulo hybrid cloud storage that is the storage space actually for your home directories. Sorry, this is for the project storage. So that's the long-term storage for the project data that you have, and that's mounted as /expanse projects. So these are two different types of file systems, right? So this one has is also fast, but it has a less fast interconnect to the lasted parallel file system. And the lasted parallel file system has these dedicated IO nodes, and so these are just mounted at different mount points. And then software is installed using a SPAC package manager, and that's found under /cm/shared and then /apps/SPAC. So there's like this different hierarchy of directories that don't exist in a standard Linux system, right? One thing that is good to know is to understand is how symbolic links and hard links work. So symbolic links and hard links give you a way to refer to a file or an inode by a different name, right? So they're useful when you want to avoid writing out a full or a relative path name every time, or if you want to have a generic executable name refer to a specific version, right? So you basically create a link, and then you can use that link to refer to that file instead of having to type the full path or the full complicated file name, for instance, right? So we'll look at the differences between symbolic links and hard links. Sorry, soft links and hard links, or symbolic links, which are known as soft links and hard links in the next few slides, some background on inodes. Both types of links are created with the ln command. So if you type ln-s, you create a soft link. So you could call it soft file 1 to an already existing file. Actually, that file doesn't have to exist yet. And you create a hard link that file needs to exist. So we'll get to that later again. Then redirection and pipes are important. Most Linux commands write to the standard output, right? So that's basically the Linux, Unix philosophy that everything, right? has an input and output, and you can connect that via pipes, and or you can redirect the output. So by default, many commands write to standard output. That's just the terminal if you're working on the command line, but you can redirect the output using the larger than symbol, right? Or append with the two larger than symbols, right? So if you use the date command and you redirect it to a file name, right? So you write the date to the file, and then if you inspect it, so you'll have the date in there, right? If you execute that command again, and then look at the content of that file, you'll see it's being updated now. There's a different time in there because you've overwritten that file. If you use two greater than symbols, characters, you'll append to the output file, right? So now you have two entries in that file. So that's quite important. And then the pipe command is this pipe symbol here. It takes the standard output from the first command to the left, right? So if we look here, we do ls minus L. And then we have a pipe command here. So we pipe the output instead of writing it to the standard output. So we pipe it into the next command, right? And you can connect an arbitrary number of commands. So in this case, we would count the number of files in the current directory by piping the output of ls minus L to the WC command, the word count command, with option minus L, which basically just counts the number of lines, right? And here's an example where you would list the 3 longest running jobs and expands node exp209, right? So you use the sq command, pipe the output into the grep command, and grep for that string here, which is the node name, and then you pipe this into the head command and list only the first 3 entries. And so those are those 3 entries, and you see that, okay, these jobs have been running for a long time already, right? Standard input can also be redirected. This is sometimes useful if you want to prevent a command from listing the name of the input file. Not only, right? I mean, but that could be an example. In the example below, for instance, we want to avoid having the pipe output from WC into the cut utility, right? So if we type word count minus L, so counting the number of lines in that file, but it includes the file name, right? So what if you only want to have the number 9, right? So this file has basically 9 lines. So what we can do is we can use that command, pipe it into the cut command, minus D space, that's basically uses a delimiter. And then we only want the first field, minus F1, right? So the first field is this one here, so we get a 9. That's fine and nice, but that's maybe too long and too complicated to write. So what we could do here is you could use a different pipe command with here, or we just instead of actually so what we can do here is we can actually pipe the command, the output of the file, into the word count, right? Instead of having it as an option. So in this case, there's no file it reads from, so it just comes from the input, so it doesn't print the file name. And even shorter is, we can do WC minus L and just redirect the input that's come here from the pipe. Here we're just telling it to use the input from the file. So in this case, we don't use the file as an option, so it's not going to print the file, but the output in this case contains just the line count. So those are different ways of using I/O redirection. And now coming back here to symbolic links and hard links, and what an inode is. If you haven't heard about an inode is a data structure that stores information about a file system object. Right? So, such as a regular file or a directory. It contains the permissions, the file size, ownership, timestamps, and the location of the data. It doesn't contain the actual data, right? But it contains the location of the data. So if you know that, then you can access the data. And a file is nothing else than a link to an inode. So a file, basically, if you look at the file name, it has a link to the inode. So, the operating system knows where to find the data, and it has all the permissions, file size, ownership, and so on, right? And a hard link is just another file that links to the same inode. Okay. So it's basically as if you had two different file names for the same file, right? And now here's an important piece is that an inode, when an inode is deleted, you don't know anything about that file anymore, and it's basically deleted, and that memory on the disk is being freed up. However, an inode is only deleted when all the links to it have been deleted, right? So if you create a hard link, and then you delete the original file, the data can still be accessed using the hard link, right? It's basically a new file. It's the same file, but with a different file name. A symbolic link is a different name for the file, right? So it's not a link to the inode. It's just a different name for the file, which means that if the original file is deleted or moved, the symbolic link is still there, but it can no longer use to access the data, right? So if you have a symbolic link, you delete the original file, the file is gone. Okay. So as an example here, imagine we have two files, and now we create a hard link to file 1, and we create a soft link to file 2, right? If you use the -i option with the ls command, it will show you the inodes for each file. And so you can see that file 1 and file 1 hard point to the same inode, right? Right. So it's a hard link. While file 2 has a different inode number from file 2 soft, that soft link that we created, and it's basically shows that it's a soft link. Now, if you remove the original files that we had here, file 1 and file 2, you can still see the contents of file 1 via its name that you have created by a hard link, right? So the file is still there. If you do the same for file 2 soft, it won't find a file or directory. It gives you an error message basically because that file has been deleted. It's not there anymore, right? Only the soft link still exists. So which one should you choose, right? And why? What's the advantage and disadvantage, right? Generally, you'll work with symbolic links for two different reasons. First of all, they let you span file systems. So you cannot create a hard link on a file system that's different from the file system where you have the original file. Meaning, for instance, you have a file in your Scratch directory, and the other one is in your home directory, right? They're on two different file systems, or one is on the Expanse Lustre storage, and the other one is in your home directory, right? The only way you can link to them is you can use soft links in this case. So if you try to do that with a hard link, it won't find the file, but you can do that with a soft link, right? So here's an example here, right? You have this Lustre Scratch. You have a file there, and you want to make a hard link, and it says fail to create that hard link because currently we are in a directory that's not on the same file system, right? But you can create a soft link, and that's going to work, right? So the other thing is you can create a soft link even if the file being linked to doesn't exist. Okay. And why might that be useful? That can be useful, for instance, you have a soft link with a shortcut, and then at some time in the future you create some data for that same file name that you're linking to, and in a different point in the future it could contain different data. So it could be useful to access different data as it's being generated, process it via the same file name. So that's about hard links and soft links. Wildcards and globbing, so that's also an important topic. You're probably quite familiar with that if you've been, accessing, Linux shells. But let me just go over this briefly and tell you that, wildcards let you express a pattern for matching multiple file names. And so the most common combinations are a question mark that matches a single character, a star that matches any string, right, including empty string. And then you have the square brackets. And you can put characters, alphanumerical characters into square brackets, and then this will match multiple characters or ranges of characters that you express in those square brackets. And then what globbing is the operation that expands the pattern into a list of files, right? That's done automatically by many Linux utilities that operate on files. For instance, ls, rm, nv, cat, head, tail, and the file command. So here's an example where, here's an example file names that we have in the directory. So you see those with the ls command. If you want to see all file names that start with file, right? File names beginning with file, you just say ls file star, and you'll see all the file names that start with file, but not the file names that start with other strings. Or if you want to see all file names that begin with an F, you just type ls f star. Or if you have file names that contain GHI, you say ls star GHI star, then you'll get all the file names that contain GHI anywhere in the file name. So that's pretty simple and straightforward. Then the question mark, again, the same files. So here, if you want to list all files that start with file and then have any single character and then end in .dat, you would type files .dat. So you can see already how that can be useful. Your code, for instance, generates files, say with a string file 1, file 2, file 3, and you want to say look at all those files, delete all those files, concatenate them, or whatever you may want to do with them. And you can combine all of these, of course, with a question mark, and a star to see in this example an A plus any character plus CDE dot, and then any string. Or if you want to have all file names that have 1, 2, 3, 4, 5 characters, followed by a dot, followed by any character X and another character, right? So you would get basically here extensions txt and exe, and you get like all the files that have 5 characters in length. So that's quite useful. Then the square brackets in this case, if you have 2 different characters in there, like here alphanumerical characters, you have a 1 or a 3, it matches all the file names that contain a 1 or a 3 after file and before .dat, right? So in this case, we'll see file 1.dat and file 3.dat, but not file 2 and 4, right? Or A, B, C, etc. This is a range, so you'll get all the file names with a range of integers 1 to 3. You can do the same with a list of letters, right? So this would be all files that start with an A or a C, followed by an X, and then have any arbitrary characters, dot and arbitrary characters, right? And you can do the same as in a range with the numbers. You can have a range of letters, so A to C. So you get the files that start here with A, B, or C, right? Followed by an X, and then anything after that. And yeah, that can be quite efficiently used to for pattern matching and systematically operating on multiple file names. So another thing that's very important is aliases. What is an alias? It's basically a shortcut for Linux commands, and they're quite useful for keeping you out of trouble, right? So accidentally deleting all files, or most conveniently used to abbreviate complex commands, right? That are hard to remember. So for instance, if you do an rm star, it will delete everything. That's not great. So you might want to use an alias where you set rm should be equivalent. It should actually use this alias when you type rm. So now, you define this alias. If you type which rm, it'll return that it's actually going to use this alias rm-i for the user bin rm command. Right? So -i is interactive, so that will ask you really for every file that you want to delete. So this prevents you from accidentally deleting files. I personally like to take the risk, and I get too annoyed by having to confirm deleting files, but occasionally it happens that it will always happen sooner or later that you accidentally delete something that you didn't want to delete. Be careful with that. And then for abbreviating a long command, say for instance, you have a customized listing of Slurm partitions. We could have an alias that we call partitions. And this is whatever an sinfo command with certain options here that nobody can remember, but you figured this out one time, so you make an alias for that, and then next time, so you see you have this command defined, and it's going to run the sinfo command from this directory, but then with these options, you just have to type partitions and it will execute this command, this sinfo command. So that's quite useful. If you want to know which aliases are defined, just type alias and it will print all the aliases that have been defined, either by you or pre-configured by system administrators. Right? Now, that brings us to shell and environment variables. Those allow you to customize your environment and control how applications behave on a Linux system, right? Because they will read content of those variables. And you have to distinguish shell variables that are only known within the current shell. So you exit that shell and those variables are lost. So the content of those variables. And you have environment variables that are known globally and they are inherited by processes and shells that are launched by the current shell. So, if you launch a shell from within a shell, for instance, by running a shell script in a subshell, those environment variables are inherited. More often than not, unless you have some temporary storage, you just temporarily store something, you want to use environment rather than shell variables. And the shell variables are set using a key equals value syntax. If you're in bash, space is not allowed around the equal sign, so you must have no space here. And that's a convention, but often people use all caps values for the variable names. You don't have to do that, but it's a convention, and so you quickly can identify variable names in scripts and so on. How do you make shell variables into an environment variable? Well, you use the export command, okay? And then if you want to access the content of the variable, you use the dollar symbol, so $T will give you back the content of that variable, right? So here's an example. We set key 1 to ABCD, the string. Key 2 we set to EFGH. We export key 2, right? So we make it an environment variable. So key 1 is only shell variable. You can assign the variable content and export it in one command. You can say export key 3 equals IJKL, for instance. So now if I do an echo command, so echo basically prints anything that's in a string here, and $key 1 will give me back that content here, right? So you'll see ABCD as expected, EFGH and IJKL for key 2 and key 3. Now, if you launch a new shell, right? So just say /bin/bash, you launch a new shell, key 1 is not defined here because it was a shell variable. It wasn't exported, right? So it's empty. There's nothing in there. But now if you say echo key 2, the content is actually been inherited because you defined it, you exported the content as a environment variable. Okay, so that's what the export command does. And that is another way you can use the declare command using the -x flag to export. That's doing the same exactly as export. So just in case if you see that. With that, you have an option -r to make the variable read only within the current shell. So that's useful if you want to avoid accidentally overwriting the content of important variables. Okay. All environment variables can be displayed using the env command, so in env. So that's an example here. If you type env, you'll see the path variable has all this content, library path, etc., man path, and so on. It's just a partial output, so you get a long output, but you'll see everything that's being defined in your environment. That brings me to Linux configuration files. Linux has a number of configuration files for customizing your environment. So etc profile, etc bash rc, in your home directory .bash profile, .bash rc, and others. And it can be quite confusing. There's a hierarchy of scripts that execute these. But really, you really only have to pay attention to .bash profile and .bash rc for most cases. And the rule that you can follow is you customize environment variables in your bash profile, and you put aliases and functions in bash rc. Okay. The reason for doing that is here, it's defined here, where you have to understand the difference between a login shell, interactive non-login shell, and non-interactive shells. Oh gosh, okay, so different things. So an interactive shell is one that reads and writes to the user's terminal, right? If you can enter commands at the command line and see output, you're an interactive shell. There is an interactive login shell. That's basically if you SSH into a computer or compute node, you get a login shell because you just logged into that computer, right? Or when a new shell is launched with a ---- login option. This is where you'll usually work. So if you log into compute mode. There's also interactive non-login shells. Those are launched from a login shell by executing the bash command, like you saw before. Or if you're on a desktop system, you have an X Windows system open, and you open a new terminal, that is an interactive non-login shell because you're already logged into the system, right? And then there's non-interactive shells. They are not associated with a terminal. They're usually executed by launched by executing a script, right, or an automated process. So when you're running a script that launches a new bash shell, for instance. And gosh, so there's the order of execution for interactive login shells, interactive non-login shells, and what this means here, I have basically something on the left, a configuration file that executes another configuration file. You usually don't have to worry about anything here in these orange boxes. There's even more things for different Linux flavors. Really, what you have to worry about is just really your bash profile and the bash rc. And the bash rc is normally sources the etc bash rc, but there's logic in there that makes sure that nothing is executed twice, so you don't have to worry about that. So that's for the interactive login shell. And the interactive non-login shell, you see, it executes only bash rc, and so that's why it doesn't execute the bash profile. That's why you want to have environment variables defined in .bash profile, so it's not they're not redefined by multiple executing bash rc when you open an interactive non-login shell. So if you look for Linux configuration file information, you'll find a lot of complicated stuff that looks like this, right? All these different types of shells and how one calls another, and it's different for bash and ZSH and C shell and so on. But really, if you're using bash, let me repeat again, really you only need to worry about those two. Put environment variables in those, and put aliases and function definitions into bash rc. So really bash profile for commands that should be run only once, customizing environment variables, right? If there's something like this in there, don't edit this part, just leave it. So it's gonna get the aliases and functions correctly. And then, you have some default lines in there, and then, you can add additional things that you want to add. If you want to add something to your path environment variable, you could do this in your .bash profile, for instance. And the bash rc file, similarly, there might be something like that calls, system-wide bash rc. That's, these are set by the operating system when it's installed and by the system administrator. So just leave this in there. But you can add aliases, for commands that you use frequently, and or loading modules. If you want to automatically load modules, that goes into the bash rc as well. Then let me talk about pseudo file systems. Let me check very briefly how many slides I still have. Yeah, that's pretty good. I think another 10-15 minutes yeah, should be done. So like I mentioned in the previous talk, under Linux, everything is a file, and Linux distributions provide pseudo file systems that allow you to access dynamically generated content using the same tools that you use to access regular files, right? So like less, you can look at something, right? Or you use the cat command to just print the content to the standard output. These pseudo file systems are the proc and sys directories. And, when we're looking for hardware info, for instance, we were looking at the proc CPU info file, which is not a regular file, right? So note, if you do an ls-l, you see this has actually a file size of 0. So but it's not empty. So then if you look into proc CPU info, you actually get the information then provided by the corresponding Linux kernel modules. For instance, proc CPU info, you get the information about the processors. Then a few things about shell scripting. So you've come across shell scripting most probably. Those are just programs that are executed by the Linux shell. You have comments that you can put in there, like in any program that you write. It's always a good practice to add comments. Then you can add commands, simple commands, and then you have programming constructs available in Bash for loops, branches, variable assignment, and so on. Actually, you can use those on the command line. You don't have to put them into a shell script. So I often do this, smaller loops and so on, just type those, for one-time use on the command line. But when you want to reuse something or you have something more complex, you want to write a shell script, then make the shell script executable. And then you can just run it with a /script.sh, for instance, if you call your shell script script.sh, right? Another option to execute a shell script is using a source command, which is the same as using .script.sh. That will actually execute the source code that is contained in the shell script in the current shell and not spawn a subshell. Okay. That's why often you will see a source command in the your bash profile or bash RC shell configuration scripts to basically execute another script in the same shell, so that the environment variables that you're using from those other scripts are executed and defined in the current shell. So we don't have time to go deeply into shell scripting, but maybe a few essentials and point you to additional resources. So shell scripts can be as simple as a list of Linux commands. One thing that you usually always see is the first line has this, hash symbol, exclamation mark. This is pronounced shebang. And it defines the shell that will be used. It's a good idea to set this. If you forget it, you'll normally get the bash shell or the shell you're currently in. But note that on Linux systems, actually bin-sh is a symbolic link to bash. So even if you have something like bin-sh in there, you'll get the bash shell and not the C shell. So here's an example of a script on the left that executes the head, tail, and WC command, and then it prints basically the string, the first two lines of file1.txt. And you have the head -2, so it prints the first two lines of that file.txt, then it prints an empty line, then it prints last two lines of file.txt. That's the corresponding tail command, and then it prints the number of lines using WC -L, right? So assume we have stored this in a file that's called simple.sh. We make it executable, and then we execute it with a dot command, which is basically running the script in executing the commands of that script in the current shell. And that's what it will print, right? That string here, and then the first two lines of that file one. Actually, this is wrong. This should say file1.txt, and this one should say also say file1.txt. And here we the number of lines, right? You can define loops, right? Loops let you iterate over the items in a list. And that's very useful. The list can be defined in multiple ways, including a white space separated set of items. So a wildcard expansion, right? So we talked about wildcards. So that's basically that globbing that happens. And backtick captured output from executing a command. You will see that often what I prefer actually, instead of using backticks, is dollar and then parentheses. So let's look at this example here. So this is a for loop, and so you define a variable file, for file in, and now this is basically capturing the output of the ls command, right? So ls minus l file start.txt. So this will contain, if you type that command, you'll get all the files that start with file and end with .txt, right? Instead of using backticks, you could use dollar parentheses, right? So this will capture the output of the ls command here, right? Same way as it does here. I find this a little bit more clear to read. And then you have a do loop that basically, for each of those, file names here, will basically do a wc minus l command to get the line count, right? So you have dollar, curly bracket file. So that's basically the content of that variable. So that variable, will iterate now through each of those files names that you get from that ls command. And it will give you line count. You could do this here directly because Special understands globbing, so it will actually look into the file system and do the globbing operation for you, so you don't need to use the ls command in this case. Or you hard code it. This here is hard coded, for instance, right? I say this is what I meant with you have a white space separated set of items. So you have item 1, that's file1.txt. File 2.txt is the next item. File 3.txt is the next item. So assuming we have only these 3 files in the directory, so if you could execute all of those commands, if you any of those, basically you would have those in a script that's called loop.sh, loop1.sh. You'll get the same output, right? Assuming that the directory contains file 123.txt. Okay. So that's how you can write loops, and that can be very useful. Command line arguments are important. So shell scripts can accept command line arguments. Positional command line arguments with $1, $2, $3, and so on. $0 stores the name of the script. That's useful if you want to use a help command, or there's different use cases for that. Command line arguments obviously make your scripts flexible and reusable, right? Because you can just pass a string an option to that. For instance, here is a script that will print the character, word, and line count in a file. And so you see here, the hash symbol for comment lines. And so you would call this with counter.sh and then the file name, right? And we are just using WC with the -c, -w, -l options on $1. So $1 is now the first argument that's being passed to the script when you execute the script, right? And then it's going to print basically the $1 contains, right? And then whatever we got out here from our WC commands, as number of characters, words, and lines. So if you have a file in your directory, it's called file1.txt as an example, you could run the script as /counter.sh. So you execute the script, assuming it has been made executable, and now the argument that you pass is that file name, and that's the output that you would get, right? So now file1.txt contains, and then in this case, file1.txt had 180 characters, 36 words, and 9 lines, right? And running this in file2. So this way you can get the output for file2. So this way you can write scripts that are reusable. This is the same script. I think I can go over this very quickly. We just used input redirection here instead of using the cut command in Python. But that goes back to different ways of, there's different ways of solving one and the same problem. This one is obviously shorter, so more convenient, I think. You have conditional statements available, so the if statements. So if, and then you use a square bracket and you have some test in there, and the test is basically, can evaluate to true or false. If it's true, then you'll execute whatever statements you put in between here. And you can have an else statement, or you have an else if statement, right? So that else if statement is actually called elif, so it's literally if, then elif, then else, so you execute these 3 different types of statements. And you can have as many elif statements as you want. And each of those the elif statements must be, or if and elif must be followed by semicolon then. Yeah, shell scripts are picky about the white space that's required around the brackets, so you have to have a white space in there. And so for those conditional statements, you can use variables containing numerical values to compare, for instance, with LT, LE, and GT, or GE and EQ. I'm not going to go through all of those. You can look at those yourself again, but for instance, again, here we use 2 positional arguments, and we compare them with minus LT. So we would see is $1 is less than $2. So LT is less than, LE is less equal, GT is greater than, GE is greater equal, and minus EQ is equal, right? So if I compare 2 numbers with this script, for instance, 2 and 2, it's going to tell me 2 is less than or equal to 2, right? And that's true because 2 is less than or equal to 2. So this one will evaluate to false, right? So it's not going to go in there. It's not going to use execute that echo command, but this is true. So it's going to execute this echo command and so on, right? It should be pretty straightforward to understand. That's quite helpful. You can compare strings with a double equal sign, not equal. So this is strings are equal, strings are not equal, or string is smaller than or larger than. That's a lexicographical comparison operators for the order based on ASCII characters. Okay, and that's basically the same thing. You can see that the string 1 equals string 2. And you need to make sure that you've got a string in here. Sometimes it's better to have actually, the quotation marks. Yeah, that's the string comparison. And you can use those conditional statements also to check if a file exists, or is a regular file, or is a directory. So there's many options, but that's quite helpful, right? So here you could loop over different files with a for loop for do and done, right? So it goes, file will contain any of those names, file1.txt, temp0, and so on. And then you have an if statement here that checks first if this file exists, right? -e, then do something with it. Otherwise, the write file does not exist, right? And then you can, it will write file exists and is what? So the -n actually doesn't advance the line in the echo command when it prints the string. And then you can check if it's a regular file, -f if it's a regular file, or if it is not a regular file, for instance, it could be a directory, right? And we'll just print that, right? So if you execute the script, it will print file 1 exists and it's a regular file. Temp dir exists and it's a directory. File 4 does not exist. File 4.txt. So these conditional statements for string comparison, integer comparison, and checking for file status are quite useful. And I'm almost done. There are a few things that I wanted to mention. We didn't put those on separate slides due to lack of time, but what I wanted to mention, what's quite useful is the history command. So if you type history, you will see actually all the commands that you've executed before with a certain limit. So the history, there's somewhere a setting on how many commands are stored. You can set that to unlimited as well somewhere, but you have to set a corresponding environment variable in your bash shell. And it's very useful. You can execute, for instance, the 2 exclamation marks gives you the last command. You execute that again. Or, when you do execute the history command, so you'll get a number for all the, commands that you executed. And if you want to execute command number 247 again, you type exclamation mark 247. That's quite useful. We can actually search in the shell as well with a, you can go up obviously with the arrow keys on your keyboard, but there's also a way of searching backwards I think so the default key bindings for searching and actually navigating in the shell are the same as in Emacs, but you can change that also to VI if you're a VI user. And what I find very useful in shell scripts as well, or just while you're operating interactively in the shell, is pushd and popd. So pushd is for pushing directory. It pushes the directory name onto a stack. So you would follow that with instead of doing cd, if you change into directory, you can say pushd in a different directory. You will go into that directory, and the current directory will be stored on that stack, right? And then you can move into many other directories. You can do lots of stuff, move around. And if you say popd, you will go back. It pops basically that directory name that it has stored back from that stack. So you go back to the directory. So that's quite useful if you're somewhere in your file system and you move around and you want to make sure that you move back to the right directory. And then counters, it can be very important, when you do a for loop, for instance, that you want to have a list of numbers, say from 1 to 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or maybe just, incrementing that by 1, by 2. So numbers 1, 3, 5, 7, 9, and so on. There's the SEQ command for sequence, and you put the starting number, the increment, and the final number. And the increment can be negative, right? So you can also count down from larger numbers. Alternatively, this construct here in curly brackets. Sorry, I think I did this wrong. I think the sequence command has start, final, and then increment. And so that's a little bit confusing. And so this curly bracket expansion has this starting number, then dot dot increment, dot dot final, right? So if you want to count from 1 to 10, you write 1 dot dot 1 dot dot 10, and the increment is actually optional. If you leave it out, then the default is an increment of 1. So those are quite useful to know. And that's basically, I'm done here. So my last slide as a summary, learning intermediate Linux skills, I hope will help you to become a more effective user for advanced cyber infrastructure. And not only that, just on your laptop or as well, but of course, when you're navigating more complex tasks on a supercomputer, is very useful as well. So this tutorial provides you with the tools to customize your environment, automate tasks, construct simple workflows using shell scripts. And we covered much of what you should need to know, but there are many resources on a wide range of topics in case you have to go deeper. And this one is a very nice overview. I think the bash scripting cheat sheet here. And tldp.org has the advanced bash scripting guide. There's a lot of information there. And there are forums and tutorials at linux.org for you to look at. And with that, I'm done, and I'd be happy to take questions if there are any. Thanks for listening.